This video is part 2 of Chapter 12, Tests of Statistical Significance for Research Methods in the Psychological Sciences, PSY 222. In part 1, I was talking to you about null hypothesis statistical testing, significance testing, sorry. And I was largely giving you examples about comparing two means. When we're comparing groups, and they are independent groups, say in a natural groups kind of design where you're comparing, say, males and females, or comparing one classroom of students versus another classroom of students, or if you're using a random sampling technique where you randomly assign people to groups who are then treated as an experimental and control group. If you only have two groups, then what you're going to use is what's called an independent groups t-test. And you've learned how to do this in your Pallant homework on SPSS. If the two means that you're comparing come from a repeated measures design, what you're doing is using the same group of people, but they're measured repeatedly, more than one time, within subjects. What you use there is a repeated measures t-test, or in SPSS it's called a dependent t-test. The expectation is more and more that we are expected to report effect size when we use a t-test to compare groups, and we're reporting the significance test results, because it's an added layer of interpretation, and it, for many people, they argue it's a more precise way of describing the meaning of an effect. Effect size for t-tests are typically reported in terms of Cohen's d. With the independent groups t-tests, and luckily you've learned about this in your Pallant homework. When we're comparing, say, a treatment and control group, what we're doing is we're taking the difference between the means. So the treatment group has a mean, the control group has a mean. We're taking the difference between those means and dividing it by the standard error of that difference. The formula represents how the t-statistic is calculated in this way. I only show this to you, it is in your textbook, but I show it to you because it helps me to visualize what is this statistic actually doing. For every participant in each of the two groups, you calculate a mean across all of the individuals in that group. So you've got the mean for group 1 and the mean for group 2, and you're going to subtract the mean of group 2 from the mean of group 1. That creates a difference score for those two means. There's also always going to be some error associated with the mean difference. So you have that mean difference and you calculate a standard error. So we're taking the difference between the means and dividing it by the error in our calculations of those differences. What we want to do is then we take our t-value and we want to determine the probability associated with that statistic so that we can make a statistical significance decision. If the value of t that we calculate, and remember how in your SPSS printouts or output files, there's usually a table that you're given. In a t-test, you'll have a significance value, that's the p-value, but there's also a t-value, that's the observed value. And then you want to see if your observed value is going to be is going to enable you to reject the null and make a conclusion that the difference in the means is statistically significant. And then that, as your authors say, would allow you to conclude that the independent variable had a statistically significant effect. If, however, your observed value comes out and the p-value is greater than 0.05, you're not going to reject the null hypothesis. You're going to pause. Basically, your authors, as they argued and as I presented in part one, you don't just say, well, there's nothing there, period. You do withhold judgment. There could be methodological issues, a whole host of reasons why you don't find a statistically significant result. One step you want to take at that point when you don't get a significant result is you do want to look at the power. If your sample size is weak, that can help you to make a decision about whether or not to redo the research and have a larger sample size. You may want to ask some more questions about the sensitivity of your measure, and a variety of other methodological questions could come to mind. The Cohen's d measure, when you're doing an independent samples t-test, remember that t looks like this, where in the numerator you have the difference between the means, and in the denominator you have the standard error associated with that difference in means. The degrees of freedom, and we haven't talked much about degrees of freedom in this class because it's not a statistics course, but what these statistics are dependent on our understanding what the degrees of freedom are. You have the number of subjects in group 1, the number of subjects in group 2, and how many groups are there? There are 2, so the total n minus 2 is your degrees of freedom. The Cohen's d is based on this corrected number of subjects, essentially, the total number of subjects minus 2, that's the square root of that, and 2 times the t is in the numerator. That gives you basically, you're taking into consideration the number of subjects, you're taking into consideration the value of t that describes the difference in the means, and that gives you the effect size. So when you're looking at the t statistic, it's not taking into consideration the fact that you have a certain number of participants, and D allows you to do that. Now you have some familiarity with this from your Palette homework. D values, we have to interpret them because that's what we have to do. Small effects are when you have D's of 0.2 or lower, to declare it a small effect, it has to be at least 0.2. Sorry, I misspoke. To be a medium effect, it has to be at least 0.5. To be a large effect, it has to be at least 0.8. When you could have a result from a t-test that is has a p-value of say 0.002, so it's significant. What's not appropriate is for you to say it's wildly significant or some nonsense like that, because it could have an effect size of 0.1 or 0.02 or something like that. For you to say, but for you to comment on the size of the effect, to even say that there's a small effect, you need at least 0.2. When you have larger effect sizes, that gives you greater confidence in the description of your result. So you may have noticed that in some of your homeworks, so Palette describes, there was a statistically significant difference between the groups. However, the effect size was small. And that however is extremely important in your interpretation of the result. What it suggests is it's a small difference, don't take it for more than what it is, right? So it's a way of qualifying and clarifying the result that you found. When we have repeated measures tests, the calculation is different. So because what you're dealing with is a within subjects repeated measures design, you, instead of the method that was described on the previous slides, here it's called a direct difference t, because it's a within subjects test. So if you're looking at differences in scores across conditions, say it's at time 1 and time 2 in an experiment, what you're looking at is, and we call this D bar, so it's a D with a bar over it. I'm kind of proud of myself that I figured out how to make PowerPoint type that. Anyway, the D bar is the mean of the different scores. So every participant has a time 1 score and a time 2 score, for example. And then you would calculate a different score for every participant, and then you would get a mean of those different scores. That's the D bar part. And then you have the standard error of the different scores. That's the denominator underneath. So the t-statistic is calculated by dividing the mean of the different scores by the standard error of the different scores. The significance is determined by, as we usually do, comparing the t that you calculate. And if you remember from your Pallant homework, the output table is going to have a t-value and a degrees of freedom column and a significance column. So the t-values, if you were looking it up in a table, you would look it up based on your degrees of freedom, which is the total n minus 1, and determine whether or not you have statistical significance. Now, before we leave kind of our conversation about significance between groups designs or repeated measures designs, we do need to take a breath and think hard about what do we mean by statistical significance. Because there's a difference between something being scientifically meaningful and important. That's completely different from something, a test showing you that you have a statistically significant result. They're not the same thing. Scientifically important findings are findings that are important to the scientific community. Like right now, it is super important that we have coronavirus tests that are accurate. And in that case, that data is scientifically important. It's very significant. You could have research that shows, statistical significance related to the accuracy of say, a virus test. If it wasn't that important to the scientific world, maybe there are a whole bunch of tests that already do that. It's just not as meaningful or important. So one factor that determines whether a scientific finding is meaningful to the scientific community is the nature of what you're studying. Some variables that we're looking at are simply more valuable for us to understand. Like with coronavirus research right now, it's devastatingly important that we understand it. It also depends on how, on the quality of the work that you've done. How rigorous were your methods? Were your methods those that are well understood, well valued within your field? Were your methods appropriate? Was there a lot of mess and inconsistency in what you were doing? If you could have a statistically significant result, but if it was a crap study, it's not important, then it should be rejected. And there are other criteria. You could have a statistically significant result, but the effect size is small, then it may have very little meaning in a scientific sense in terms of the ability of the finding to add to our scientific understanding of a particular behavior. Now we also have to throw in here the fact that statistical significance is not the same as practical significance. Practical significance has to do, what does this finding mean for the real world? Or if we're talking clinical significance, what does this mean for actual clinical practice? Practical significance depends on a whole lot of things. Most importantly, the degree of external validity that you have. And remember what external validity is. That's the degree to which you can generalize your findings to novel situations, to other populations, and across time. Notice that also effect size matters here too. If you have a finding, even if there's decent external validity, if the effect size is small, that may limit considerably the practical impact. Let's say you have a classroom teaching method and you find a significant difference in reading scores between your two groups. Either the group that got the treatment and the group that didn't get the treatment. You find a statistically significant difference, but the size of the effect is very small. So maybe the boost in reading scores is maybe 2 or 3 points. That doesn't have practical meaning. It's not going to be big enough to have a meaningful impact on how well those kids are actually reading in the real world. Another thing that affects practical significance, you may find a statistically significant result, but if you can't implement the treatment that you have discovered in a practical way, it really doesn't matter that you found that you can produce this effect. It may just be limited to the fact that you can't make it happen in the real world. Now, when we're comparing means, either in the context of independent groups designs or within subjects designs, you have to keep in mind what you're actually going to do with your data analysis. And eventually, you want to be able to make some kind of claim about your hypotheses concerning your behavior of interest. When you have a choice of what kind of analysis to run, it's always best to choose the simplest test, the most straightforward test. Just because you can do a MANOVA doesn't mean you should. If you can answer the question with a simple t-test or an analysis of variance, you should use the simpler test. Second, when you're doing NHST, you have to understand the weaknesses of that approach, what it does and does not allow you to conclude about your findings. It may seem silly, prohibiting you from using the word prove, but what that shows is that you respect the limitations of the NHST approach. And then finally, your authors recommend, and I agree, that you have to get out of the rut of just interpreting p-values and become more complete in describing your results. And that includes effect sizes, it includes confidence intervals that are connected to your test results. Because really what your job is as a scientist is to present comprehensive results to your reader. And that's your responsibility as a communicator of scientific results, is to give them all of what you have so that they can draw the right conclusions right along with you about your data. Now, I did throw this in here just to remind you, there are norms and expectations about how we write about findings. And it includes things like, where do we put the italics and how do we space things when we present things in type. Your authors provide you with an example of a paragraph. Pallant provides you with examples of paragraphs. I've showed you this in my various tutorials. It's really helpful if you learn how to do this and do it reliably. When we present means, and it's expected that when you're doing a t-test, you present the means and the associated standard deviations. If it's a small number of means that you're going to present in your paper, you can do it in the text of the paragraph. If you have a bunch of t-tests that you're running, lots of means, you can put them in a table. And if that's the case, you don't need to repeat them in your paragraph. But this is an example of how you would put the means and the standard deviations. That's the descriptive statistical information associated with a t-test. Notice that the letters SD for standard deviation are in capitals and they're italicized. Notice that there are spaces around the equals sign. Same here. The T statistic, the T is italicized, the DF is in parentheses, there's a space around the equal sign. You give the T value followed by a comma. The P is italicized, there are spaces. In this case, this is probably an SPSS result of 0.000, so they're using the less than sign. The D is italicized, there's a space around the equal sign, a comma, and then the reporting of the confidence intervals. And then usually a sentence that gives a verbal description of what you see. That concludes part 2.